Hello everyone and welcome to the SensiML webinar Creating Custom Acoustic Recognition Algorithms in conjunction with Silicon Labs. My name is Chris Rogers, I'm CEO of SensiML, and today I have the pleasure to introduce your two primary speakers for this webinar. First of which is Chris Narowski, who is CTO at SensiML, and secondly is Matt Maupin, who is Senior Marketing Manager at Silicon Labs. Over the course of the next 50 minutes, we intend to walk you through a full example of how to build an acoustic recognition algorithm that can run on an embedded microcontroller. Chris Narowski will start off with a brief introduction on SensiML's software for building these types of algorithms, and Matt Maupin will provide a brief overview of Silicon Labs' ultra-low power SoCs with AI acceleration built in. The majority of our time here will be spent on a hands-on style tutorial for how to build an Edge ML model for acoustic event recognition for either sounds of interest or voice commands. We'll be using a consumer smart lock application as our example to work through, and we'll show you how to collect and label an audio dataset for purposes of building an ML model, how to convert that dataset into a working model and then subsequently into optimized firmware appropriate for running on a low-power microcontroller, and how to perform all of the above with little or no data science expertise thanks to the power of AutoML. At the end of our talk, we'll have approximately 10 minutes to go through Q&A. So as the webinar is proceeding, if you have any questions, please use the Q&A button to log your question, and we'll get to it at the end of the webinar. Before I turn things over to Chris Narowski and Matt Maupin, I wanted to provide a super brief introduction on SensiML if you're not already familiar with us. We are a software solutions provider for machine learning at the IoT edge and have been in existence since 2017 as an independent tools vendor for building time series sensor-driven recognition models that run on microcontrollers for the kinds of applications you see here and then some. Popular ones that we support would be things like acoustic event detection, activity recognition from IMU and accelerometer data, anomaly detection for either industrial controls or machinery for predictive maintenance applications or otherwise, gesture recognition, voice and keyword recognition, and vibration classification for machinery, to name just a few. If you're interested in learning more, I would invite you to visit our website at sensiml.com, as we'd like to dedicate the majority of our time here to walking through the workshop example for acoustic recognition algorithms. And with that, I will turn it over to Chris Narowski.
Hello, I'm Chris Narowski, the CTO of SensiML. The SensiML workflow can be summarized as follows. Step 1, data collection and labeling. In this step, the developer collects raw sensor data and assigns corresponding labels to create a supervised machine learning dataset. The dataset should encompass a wide range of variations in sensor data that the model might encounter in the real-world scenarios. The tool used for this task is the SensiML Data Capture Lab. The Data Capture Lab streamlines the process of collecting data and minimizes labeling errors. Step 2, model creation with Analytics Studio. Once the labeled data set is ready, the developer moves on to building a working model using SensiML pipeline templates, the SensiML AutoML engine, or building a custom pipeline from SensiML blocks. This step is performed using either the Python SDK or the Analytics Studio, which is a web-based interface. Both interact with our backend Cloud ML engine. The Cloud ML engine automates the process of model creation, significantly reducing the time and effort required to create a machine learning model. Step 3, code generation, test, and validation. Any model built within the SensiML Analytic Toolkit can be turned into a knowledge pack, which is automatically generated firmware code that's optimized to run on an embedded device and contains all of the steps in the pipeline. The SensiML workflow emphasizes an iterative approach where the steps are performed in multiple passes to achieve continuous improvement. Building the initial model often reveals opportunities for refining the testing methodology and identifying unaccounted variance sources. These insights drive further data collection and iteration, maximizing the performance of the machine learning models. Let's explore the knowledge pack, which is a crucial component of SensiML's technology. After creating and training the model in the cloud, you can use SensiML's code generation to automatically create a knowledge pack. The knowledge pack is firmware that includes all of the necessary components from your pipeline: signal preprocessing, event triggering, feature transformation, and machine learning classification. The knowledge pack is available as an ML library, either in full source code or as a compiled linkable library. It offers a simple API which allows you to make a single function call to pass in sensor data and receive classification results. Additionally, there are advanced APIs that provide further fine-grained control over each individual step of that knowledge pack firmware. The library is optimized for embedded devices, meaning it avoids dynamic memory allocation and leverages hardware acceleration features like SIMD and AI hardware accelerators, such as the Silicon Labs matrix vector processor. Now I'm going to hand it over to Matt, who will delve into the Silicon Labs SoC family specifically designed for ML applications.
Thanks for the opportunity to talk about our AI ML solutions at Silicon Labs. We're going to take a look at some of the common applications that we are seeing for ML at the edge. One of the first ones we see is use of sensors to collect data. This has been going on for a while, but of course it's been using the cloud, so they've been collecting the data and sending it up and processing it. Now with this, we could actually do the ML inferencing at the edge and actually look for anomaly detection in order to see what's happening. This can be used for things like acceleration sensors for fault detection, or even multiple sensors like acceleration, voltage, and temperature to help detect maybe a possible failure in a motor. The next one we see is audio. Now, the first one we're talking about is really around pattern matching. So this is things like glass break detection, as well as what we're going to be looking at today for acoustic recognition. You can see that between sensors and these low-end audio applications, the amount of resources is fairly similar. You need a little bit more flash and RAM, but the operations per second is pretty low. When we jump into this next application, though, for voice, it actually, you can see a pretty significant increase in the operations per second required. In this voice, we're really talking more about, voice tagging or simple command words. We're not talking about something like an Alexa. So, you can see here that, the operations goes from about 5 to 6 for the previous ones to about 40 million ops per second. RAM usage is still fairly low, though. And then in this final application for vision, what we're seeing is a pretty significant jump in both the RAM requirements as well as the operations per second. In this specific application, what we're looking at is for things like maybe presence detection or people counting, etc. So you can see based on the amount of work you're trying to do at the edge device, your resources go up. The good news is all this is capable of being done at the edge device. But what you want to do is you want to optimize the edge device both for processing and for current consumption. And that's one of the reasons we developed our matrix vector processor. This is really just an AI ML accelerator that handles a lot of the complex multiplication, etc., that's required for inferencing. And this handles the data. And the key thing is it really offloads the MCU. So the MCU could actually be in a sleep mode, or it could be off doing something else. And through benchmarking, we've shown that we can get up to 8x performance in inferencing over a Cortex M, and at about a 6 of the power consumption. So we actually have 3 different platforms that are supporting MVP, and I'll talk about these. But the key here is we have a 2.4 gigahertz, we have a sub-gigahertz, and we have a Wi-Fi. The reason for this is that really AI ML at the edge is protocol agnostic. What I mean by that is, we're going to see these type of applications be done on things as simple as Bluetooth. Maybe we're doing them on sub-gigahertz networks that need proprietary or long range, as well as Wi-Fi solutions as well. So if we look at our first solution, this is the EFR32XG24. This is a multi-protocol 2.4 gigahertz device that can run Bluetooth Low Energy, 802.15.4 for things like Zigbee, as well as Matter. And it does have enough flash and RAM to run all 4 of the applications we mentioned earlier. So it's got about 1.5 mega flash and 256K of RAM. It is designed to be low power, so it is designed for battery operation. And as I mentioned, it does have this AI ML hardware accelerator on it. The next product is a product we've announced. It's the XG24. This will be actually in production in August. This is a dual band device. What I mean by that is it's got support for both 2.4 gigahertz Bluetooth Low Energy as well as sub-gigahertz. The sub-gigahertz could be used for protocols like Z-Wave, it could be used for YSUN, as well as proprietary protocols out there. And again, it has enough flash and RAM to run the 4 applications we talked about. And this is also designed to be low power, so it is ideal for battery-powered applications. And then finally, we have the SIWX917. This device has been announced, it's sampling, and it'll be in production later this year. But this is a 2.4 gigahertz Wi-Fi SoC. So what I mean by SoC is that it is capable of running Wi-Fi, the protocol, and even the application all on this single chip. And it does support, up to 180 megahertz ARM Cortex. But even with that, we want to offload this. So it does have the AI ML hardware accelerator. And you can see from the flash and RAM, this is ideal for that. It provides enough flash and RAM to support those applications we talked about. And again, if you look at what we're doing across the board, this is designed to be low power. It's really for Wi-Fi clients, and they can be battery operated. So a common use case for this where we see this device is things like door locks. So no matter what you are in your development, what you need, you'll be able to do development on these 3 different platforms with a multiple of different development platforms, all supporting AI ML at the edge.
Thanks for that overview, Matt. Switching gears, let's focus in on acoustic recognition for edge AI applications. We've come across a variety of use cases at SensiML in the audio realm, not just keyword, but a lot of times they are smart home appliances or industrial manufacturing, where using the acoustic signal can really improve the ability to detect different events. We've also gone further than just using an acoustic sensor, but including other sensors such as vibration sensors in the form of an IMU, and by combining the two, are able to really improve the model results beyond what audio alone can provide. To go into more detail, we're going to build a model for a smart door lock as our hands-on example. For the demo, we will strictly focus on building a model targeting audio alone. For a more in-depth tutorial, you can follow the link in the QR code. The tutorial in the link goes into additional details, demonstrating how you can combine audio and vibration from the IMU sensor to further improve the overall performance and reduce the false positives. Let's break down the steps for building high-quality classifiers rapidly for edge devices. Step 1, data collection and augmentation. Start by collecting your dataset. Once collected, utilize augmentation techniques to tailor the data to the environment in which your model will operate. For instance, overlaying TV sounds on keyword utterances can mimic an environment with the TV on, or adding crowd noise from a showroom floor can simulate a noisy setting where you may be giving your demo. Additionally, you can augment the data itself by altering the pitch, amplitude, and frequency. Choose the right augmentation strategies carefully, as they're crucial for achieving good results in your final model. Step 2, select a foundation model. Foundation models have fixed architecture and inputs and are trained on large data sets to generate effective filters for class discrimination. You can think of foundation models as another form of augmentation. They help reduce training time and the data set requirements that you need to collect. Step 3, transfer learning and feature augmentation. Apply transfer learning techniques to update specific weights of the foundation model, tailoring it to your application. You also incorporate feature augmentation techniques to prevent overfitting, improving the model's performance. Step 4, quantization aware training, or QAT. QAT is a strategy that improves model performance by training on integer values instead of the standard floating point values. QAT has been shown to enhance accuracy for models employed on edge devices. And step 5, post-training quantization. We utilize post-training quantization to quantize the model weights. This reduces the model size, making it more suitable for edge deployment, as it can take advantage of SIMD instructions and reduce the overall memory footprint. By employing these strategies, we can swiftly build high-quality classifiers for edge devices. The knowledge pack pipeline we will create in this tutorial will look like this. Raw sensor data will come in, we'll apply some sensor filters and pre-processing, event triggers and feature transformations, which will result in a spectrogram that will feed into our neural network. The neural network will be a combination of convolutional filters and fully connected layers. And now let's go ahead and jump into the demo. Before we get started on the demo, I want to make sure you have access to all the tools. So as a prerequisite for this talk, you should have already signed up for an account and downloaded the Data Capture Lab, as well as installed Simplicity Studio. I won't go through doing all of that, but I will give a quick shout out to how to get to our sign up page. So if you go to SensiML.com, our website, you can click on free trial and you can sign up for a community edition account, which will give you access to this Data Capture Lab and the Analytics Studio with enough CPU credits to get through these demos that we're going to do. So first, I'm going to jump over to our documentation. So you can go to sensiml.com/documentation. And if you scroll down to supported devices, you'll see the firmware for the Silicon Labs XG24 dev kit that we're going to be using today. And inside this documentation, you'll see a link to the accelerometer gyroscope firmware, as well as the microphone firmware. So you can just go ahead and download the pre-built hex download for the capture. Or if you want, you can click on the source code link, which will take you to the GitHub, which has a project for the microphone data capture firmware. And you can build that yourself for the board and flash it yourself. So I've already gone ahead and flashed my board. If you haven't done that yet, you can open up Simplicity Studio and just go ahead and go to the binary for you can go ahead and click the flash, find the board that you want to select, and then navigate to the hex file that we downloaded, and just flash that to the board, which will load the microphone capture firmware. Once you've loaded the microphone capture firmware, next we're going to go to the Data Capture Lab. In the Data Capture Lab, I've already created my project, but you can go to the link that we'll supply that has the project download and download the project yourself and import it. So when you download that project, you would go and click Import Project, choose the .dcl proj file, drag it here, and it'll import that file into the Data Capture Lab its own folder, as well as sync it by uploading it to the cloud. So I'm going to go ahead and click on Smart Lock Copy, which is the name of my project. Right now it's just updating and syncing. And so if I click on the Project Explorer, what you'll see on here is all of the files I've already captured. And so I've captured and labeled about 713 different files for this project. And so what I'm going to do is show you first how you can capture your own data. So we'll go ahead and switch modes here, and I'll click on the capture button. And I'm going to connect to the XG24 dev kit. So if you open this project, this will already be there. So I just need to click connection settings and click scan, which will scan the serial ports, because that's how we're connecting to stream the audio data. And 2 ports will pop up. I know from my board, I need to connect to COM17, so I'll connect there and click done. And this is going to connect to the board over what we call a simple streaming protocol. And the simple streaming protocol is great for streaming sensor data. You can do multiple channels, and it has built-in handling for package drops, so it can recover when there's a package dropped. And so what you're seeing here is the sensor data being streamed in right now from the XG24. So I'm just hold it up here. So you can see I'm just connecting it to the computer using the USB serial port. And as I'm talking, it's picking up that over the microphone, which you can see live streaming in. So for this, we will go ahead and make a test. So I'm going to name this text file open. There's a number of different ways that you can go in and set your file settings for how you'd like the name to be created. And then I'm going to specify the board. I don't actually have an enclosure, so I'm going to click Add Metadata. And demo unit, we'll edit this one and say no enclosure. Say done, done, done. And so in this case, what I've done is I've added a metadata to the project. So I'm keeping track of the context for which the data is generated. And I'll add this to my testing set. And what we'll do is go ahead and click the Start Recording button, which is going to start recording, saving the sensor data. So I'm just going to go ahead and do some knocks. And then I'll say open, open, and click the Stop Recording button. And after I click Stop Recording, it's going to, again, bring up this confirmation screen for how I want to save. So this is what the file name is going to look like when it's saved. This is what the metadata is going to look like. And I'll go ahead and hit save. And it's also going to upload this file to the cloud as well. Okay, so now that that file has been created, I'm going to go ahead and switch modes back to Label Explorer. And so I'll come here and sort by upload it. And we can see here's the open 002.wave file that we just created. And I'm using a session, which is an auto session, which means it has a built-in algorithm to automatically detect events that are happening, not classifying them, but just detecting them in this case. And so what I'm going to do is I'm going to right click here and say segments. I'm going to go ahead and open this file so you can see what it looks like in the label view. So you can see here is the audio that we captured. I can zoom in, move this around, look at it different ways. And then at the bottom is the spectrogram for this audio file. You can go in and change all of these settings to make the spectrogram look different, to make it easier for you to label. I can hit play and I can actually hear the audio. You may not be able to hear it in this recording, but I can hear it. So I can listen to it as I record it. And then the other thing I'm going to do is I'm going to automatically add segments to this. So I'm going to click the play button here, which is going to run an algorithm to detect the different events that are happening right here. And so right now it's just running this capture file through, and it'll return very quickly the segments that it finds for this segmenter. And you can build your own segmentation algorithms within this toolkit. You don't have to use the pre-built ones. So you can see it came back. And so if I were to come over here and play this sound, this was just me randomly talking. So I'm going to hit Control E, and I'm going to label that as unknown word. So we're already starting to build out our negative examples. And then here, these were all knocking. So I'm going to hit there. I can hit this edit button and say these are knocking. And then right here, I believe these were me saying the word open. So I'll click on both of those, right click and say open. And so now we've labeled this file, and I'll go ahead and hit save. Okay, so to do this, we've used the data capture lab to collect the sensor data. And then we went ahead and used it to also label that sensor data using an automated event detection algorithm to make our lives a little bit easier. So now this data set is ready to be used as part of our training or testing process. If I open up the Project Explorer here, I can see all of the metadata. So one thing I usually do when I'm building out a project is I'll decide which data do I want to be part of my training procedures, and which data do I want to hold out for my test, which is a pretty standard machine learning practice. And so here I have a metadata for test and a metadata for training. And you can very easily change which ones you want. So if I wanted to change the metadata, I come in here and say edit, and I could switch the set that I'd like them to belong to. And so one other thing I'll point out for this project is another strategy that we often use for generating of data augmentation strategy is we actually will use generative AI to create a number of different utterances. And so for this example, I created over 200 different utterances using the word open, and they're all using different accents, both male and female, from different generative AI algorithms. And this is a really great way to augment your data set. Instead of needing to go out and collect a whole bunch of words that's people saying open, you can generate a very large corpus of data very quickly that way. So now that we're finished labeling the data, let's go ahead and jump over to the machine learning side of it. We've built out our supervised data set, and now we want to build our model. So to do that, I'm going to go to the Analytics Studio. It's a browser-based application, so you can go to app.sensiml.com or .cloud and go ahead and log into your account. And once you log in, you should see all of the projects that you've created so far in this UI interface. So I'm going to go ahead and open up the Smart Lock copy. And so here's the project overview. So it tells me how many captures I have, which is the files, how many queries, pipelines, and models I have, and the total number of segments. So the first thing I'm going to do, I'll click on the data manager. So inside the web UI, you can also go through and look at the data and move your labels around. So just to open up one of these files. And let's see, change the session to this auto session right here. And so you can see here's one of the files we uploaded, and we can see the segment labels that we put down. You'll notice that I can't change the position of these. That's because it was created using a auto segment algorithm. But if I switch over to one of our manual sessions, I could very easily create a new segment here and move it around. Similarly, you can do that in the data capture lab as well. So let me just go ahead and discard that. And I'm going to jump over to the auto session again. And so again, this is an overview of all of the captures that we have. You can look at it in the UI interface as well. But the first thing we want to do next is to create a query. So I've already created one, but I'll walk you through the steps to create your own query for your project. So you would come to the Prepare Data tab and click on the Create Query. And so I would say Demo Query, and I'd select the session that I want to create the labels from. So I'll select the Auto Session 8K because that's where I added mine. Typically, you can think of sessions as a way to version your data. If I were to jump back to the Data Capture Lab and say all of these that I wanted to let's see, so segments, say I wanted to copy these segments, I could copy them to a manual event. So I'll create that session. So I'm going to copy segments from auto session 8K into another. I can select that, and it's going to copy all of those segments into this one. And so now if I open up this file here, I can switch to the manual, and then I can go ahead and move this around or change the size however I'd like to do it. So we'll use those to version data, to make different copies of data, to try out different segmentation algorithms. It's a very useful technique for managing your data set. So the next thing I'll do is I'll select the label that I want. You can have more than one type of label in your project, but by default, one is created with labels. I'm also going to go ahead and select the metadata set. And for source, I want channel 0 from the microphone. And I'm going to create a query filter from set, and the source is going to be train. So this query filter, when I use it this way, is only going to pull in data that has metadata train from my set, and that's how we are able to create a query that only includes that training data. So when I hit save right here, it's going to create this query. The status says not built, so we haven't actually built the query yet, but we've created it. So if I were to say rebuild, it would build the query cache. I'll go ahead and click manage so you can see what that looks like. So when I open up this screen, it's going to give me a summary of this query. So you can see here's the segment length distribution for all of my segments. They're all the exact same length in this case because I use that auto segmentation algorithm with an 8K sample window size. And then I can see the label distribution. So this is the number of labels for each type of event that I've labeled. And in this case, the label distribution by samples is the same because they are all the same length of segment. And then I'm going to just go ahead and click this build cache button. And so what the cache does is it takes the query at its current state and it creates a cache of it. And that is a way to version your data set for a model. So if I were to go and change some labels, change anything about the model, it would not actually update the query cache until I rebuilt the cache. So it's another way to speed up building models, but as well as give you more control over being able to go in and edit data sets without disrupting any of your model building process. Okay, so now we've gone ahead and built our query. So we pulled in all of this data from our training set, and now I want to go ahead and build my model. So I'll click on the build model screen. And as I mentioned earlier in the talk, we have a number of different ways to build models. So there's the create the new pipeline. So I can create a new pipeline for AutoML or a custom pipeline, or I can make use of these pipeline templates right here. And the pipeline templates are geared towards specific types of applications, and we've already built out the pipelines to include certain feature extraction and pre-processing steps. So for this one, I'm actually going to click on the keyword spotting template here. I'll click next. And so all of my data is 8,000 samples long. So I'm going to select this foundation model right here, or this pipeline template model for 8,000 samples. And I'm going to give it a name. So I'll call it demo pipeline. And I'm going to select my demo query as well. And this just gives me some summary information, and I'll go ahead and say create pipeline. When you create pipeline, it brings you to the pipeline builder create screen. So here, the first thing it's asking me is it's saying you need to just go over the settings for your segment filter. So the segment filter energy threshold is used to start classification. So we want to basically set this so that we ignore sounds below a certain threshold. And that allows us to filter noise. There's a number of different tools built in, such as VAD, so like voice activity detection, or this energy threshold or frequency threshold filters. So in this case, the default is set to 500. So if I jump over to the data capture lab and I look at my data here, I can see that this one's actually going up to about 5,000. If we go to this file that we just created, take a look at that. We can see kind of the range here. With me talking, the microphone's pretty far away, so it doesn't pick it up, but it's still around so it's around 300 range. When I said open into the microphone, it's around 500 to 1,000. So we could probably set this filter around 1,000. Of course, we can go into a little bit more detail. Let me switch here. and look at the some statistics for this, so I can see the min minimum 25th percentile, medium 70th percentile, and maximum values for any of the segments that we want to look at. So I'm going to go ahead and set this to 1,000. That seems reasonable. And then these other functions, you can look at what each of these are doing by hovering over on this. And so this is the UI mode. We also have a JSON editor. So if you want, you can come into the JSON editor and specifically edit the values here. You can look at the documentation to see what they do. And so while we have this front end UI for looking at all of the steps in the pipeline, when the pipeline's fully constructed, really it's a JSON. And so we give you the ability to edit that JSON in here as well. So let's take a look at what the pipeline steps are. So up top, we have these pipeline settings. This is a single pipeline with custom parameters. So we're not actually using AutoML in this case. We're just going to run this pipeline. It's going to use transfer learning. So the first thing is we have this input step, which is our query that we selected. And then we're going to do windowing. So windowing is a sliding window. In this case, the parameters are the sliding window size is 480, and it'll slide 320 samples every time it does a classification or a feature extraction. So we're going to have window size 480, slide 320. So I have 320 new samples every time we do that. And so I'll hit cancel there. We already looked at the segment entity threshold filter. So we'll look at the feature generators next. For this pipeline, we are using the MFE, which is frequency extractor. You can look at more information here. Because we're using a pipeline template, we don't really want to change anything about this pipeline in terms of feature extractors because the model we're using expects a certain input. But I'll just go ahead and show you that we have a number of features built into the toolkit. So I could come in here and I could go through and add a number of features this way and specify any of the parameters for them. You can also add your own custom features to the pipeline as well. I won't go into that right now. And so we'll go ahead and cancel that. So we have feature generator. Then we do a min-max scale, which is going to quantize those features. And then we have a feature cascade transform. And so what that's going to do, the feature cascade, you can think of it as stacking these blocks. So every time we have a window of 480 coming in, we extract the MFE features, and we're going to get 23 features when you do that. And then we're going to stack them 24 times using the feature cascade. So the number of cascades is 24. So we're going to end up with a 23 by 24 size feature vector before we feed it to the classifier. And so after the feature cascade, we call the TensorFlow Lite for microcontrollers. We set that as our classifier, and we're using the transfer learning training algorithm. So if I click the edit button here, I'll see this is the base model that I'm using. We can edit some parameters. So here's using the softmax as its final activation. That softmax is good for this. You can add some dense layers. You can specify dense layers that you want to add as in a list here. Then there's a number of other parameters that we can set here that will change how the model is trained. And so one of the important ones to look at is the augmentation here. So for this one, we want to add the random masks, random frequency mask, and time masks. We want the random bias and the sparse noise. And those will just help our model prevent it from overfitting or training to the data too closely. Set that to 0 and hit save. And then finally, the way we're validating the model. So we're using stratified shuffle split with a validation size of 0.2. So what that means is it's going to select 20% of the data and hold that out for validation as it's training the model. So we can get a good idea when we look at the graphs for the model, how that gets trained. There's a number of other built-in validation methods. You can look through those and see which one suits your particular need for your model. Yeah, and so once we've set up our pipeline, the next step is to click Optimize. I'm just going to go ahead and jump over to the model I've already run instead of running this one for the tutorial. So I'll open up this one. And so what you'll see after the model finishes running is it'll say, here's the model result. It'll tell you the accuracy, the size of the classifier, the number of features, and these other parameters. And I can click here, which will bring us to the Explore Model tab, which will load up some more information about the model. So here I can see the training and validation values for the model that I had. I can look at some feature visualization, which can allow you to look at two features side by side and get a better idea of how the classes are separated out by those features. You can dig into the feature summary, which again gives you more information about, for each feature, it's going to provide you an overview of what that looks like when compared to the other features in your data set. And then the model summary is here's where we can look and see how the model was trained. So here's the training accuracy and the validation accuracy, and as a function of the number of epochs, as well as the loss as a function of epochs. And then the pipeline summary for this model, it tells us how this model was trained. And for the knowledge pack summary, it tells us what's actually going to go on the device. And let me jump back to the build model really fast. So I left out one step when I was going through. So let's jump to the demo pipeline. So if you noticed, if you remember from our query, we actually have a number of different data sets in there. But when I do the model training, I don't want all of those. So what I'm going to do is I'm going to use this feature grouping step. So I'm going to go ahead and click add there. And I'm going to do combine labels. And so I want to create this unknown label here. And I want to put unknown in there. Let's take out knocking, unknown word, blocking, open. So we have these other classes, which are key, noise, click, clapping. Those are all negative examples. And so I want to add them all to the unknown label. So this is a strategy where you can accurately label your data when you're collecting it. And then when you go to build the model, you can just combine those labels into a single value of unknown, which I could have just labeled them all unknown when I was labeling the data, but then I'd have data that wasn't labeled correctly. So we prefer to do this strategy where we label the data accurately and then modify the labels when we're going to train with it. Go ahead and hit save there. So another thing I'll point out is, so for this pipeline right here, if you look in the link to the that we sent you to download, you can actually come and click import pipeline, and you can import that pipeline into your project, that pipeline JSON. You can just drag it over here and import that instead of going through and building it yourself to get the exact same results I'm showing you. So let's jump back over to the Explore Model tab. So we went through all of that. The Test Model tab, so we can come in here and we can actually test the model. So how I would do that is I would just filter out test, and then I can look and see which files do I want to test against in this test set, and I'd click on that file or more, and I just say recognize. And what that's going to do is it's going to build, generate the firmware for that model and run it in an emulation mode in the cloud. And it's going to pass this sensor data in, and then it's going to compare it to the ground truth that I had labeled. Finally, the last step is now we have our model. We're ready to go ahead and download it. For this tutorial, you're going to want to select the Silicon Labs XG24 platform, and that'll give you access to the Silicon Labs MVP AI Accelerator right here. So you could pick CMSys or you could pick the MVP AI Accelerator. And then you can pretty much leave everything else the same. Sometimes I like to download test data with it, and you can use test data as a way to validate if the model is working on a known waveform. So instead of feeding the data instead of like turning it on and running it through the microphone, I can just go ahead and download this WAV file. It'll be included as a header file, and you can just run that through the model and validate that it works exactly how you're expecting. So it's a really nice strategy to debug any issues you're having with your model. So I'd go ahead and click the download button here, which is going to go ahead and compile the knowledge pack. And once that's done, it's going to return a zip file to me that I can open up and include in my project. I'm going to go ahead and jump over to Simplicity Studio now and show you what that looks like. So here is the SensiML XG24 microphone recognition project. And let's jump over to, so the microphone recognition firmware source code you can find here. So you just go ahead and clone this and add it to your project. And once you've done that, there's a knowledge pack folder inside that project, which has the lib file and the application files. And you can just go ahead and copy those from the downloaded knowledge pack over to here. And you'll notice it already has the libTensorFlow microlight and libSensiML already compiled in. And then all you need to do is go ahead and build that knowledge pack and flash it to your device. And so let me show you, before we do that, one other strategy. Before I flash the device, I want to go ahead and show you in the data capture lab another trick that we can do. So I'm going to switch back to capture mode. I'm going to come to test model. And so in test model, change knowledge pack. So here is the model that I built earlier, and you can go ahead and select it. I'm going to select the test model. That one. Select the test model session. And I'm going to go ahead and connect to my XG24 dev kit. So the data is going to start streaming there. And then I can connect to the model like that. And so when you connect to the model, now while the data is streaming in, it's going to emulate the model on Windows. So you can get a live view of what the data looks like along with the model results. Let me see. Open. So you can see right there, it actually ran the classification. In real time, I can see what the data looks like. And I could also go ahead and start recording that. So if I start recording, open. So open's working okay, but there might be another word that sounds similar to open, but it doesn't, it's going to still detect it as open. So let's try. Okay. Came up as unknown word. Obey. Oh. Okay. See, that time, okay. Actually, yeah, so there's two examples where it did a misclassification. And so what we would do here is go ahead and say stop recording. I want to save this file. And then so in this case, I said open right here, but here I actually didn't say open. So what I can do is I can edit these labels and change those to unknown word and save it. And now I've gone and built a better training data set because I'm adding words that sound similar but didn't get classified correctly. So let's go ahead. So I've already built and flashed another board, so I'm going to go ahead and plug it in and show you quickly how that model works on that board. So.
Open, 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 all pan, all pan.
That concludes the talk. Thank you for listening. I hope you've learned a lot about how to create acoustic recognition algorithms and all the strategies we use at SensiML to make really good algorithms. You can work with us through contacting us. We can help you build models yourself, help you with the data collection process. We also offer a lot of custom engineering services to get people up and running. And when you're comfortable, you can sign up and start using our toolkit on your own to build your own models. So again, thanks for listening, and please feel free to contact us if you have any questions.